So yesterday, Yesterday I introduced you to the pH scale. You're welcome. So yesterday I introduced you to the pH scale. And I introduced you to the fact that this number 7 right here, that number 7 right there, is the 7 in pH 7. So a neutral solution that has a pH 7 has an H3O plus concentration of 10 to the negative 7. And that's where it comes from. Now that might be surprising to you, because you might have thought that neutral means no acid or no base, and therefore there should be nothing in there except just plain water. But that's not the case, and we're going to get to the reason why for that in a moment or two, all right? Let's though keep talking about the fact that this 7 is the power, the exponent, on the 10 with a negative in front of it. And that's what the P in pH stands for. It stands for the power or the exponent on the power of 10, right, of the hydronium ion concentration, or if you're looking at some textbooks, they might just say the hydrogen ion concentration. So let's continue our analysis a little bit. Let's continue the logic. And instead of, say, pH 7, I'm talking about a pH 3. Could somebody please tell me, what's the hydronium ion concentration at pH 3? Yep. 10 to the exponent negative 3. That's a terrible 10 right there, 10. 10 to the exponent negative 3. Now 10 to the exponent negative 3 is only 0.0001, right? Actually, I think I might even have one too many zeros in there. But that's a lot bigger than 10 to the negative 7, which has a whole bunch of zeros in front of it, all right? So notice as we move towards the acidic side of things, the amount of H3O plus gets larger. So if I move down here to 0, what's the H3O plus concentration going to be? Continue with the same logic that we just used. Yep. Excellent. Very good. It's going to be 10 to the exponent 0, right? Which is 1. Because anything to the exponent 0 is 1. So the concentration of the H3O plus at a pH of 0 is 1 mole per liter. If I have 1 mole per liter H3O plus ions in a solution, its pH will measure as 0. All right? That's kind of neat. Okay? Let's do some practice calculations. What if I had, actually, I've got to go the other way. I want to go the other way. All right, let's just move down here and practice with this equation. What I was going to say was, could you tell me what the H3O plus concentration is if I had some other funny number? Actually, I could do that. Let's put down a second equation here. So the second equation, H3O plus is equal to, what would it be in general? What have we been doing all the way along? If I said 3, 10 to the negative 3, what would it be? It would be 10 to the what? Just in general, any pH number I give you. Yep. The which? A number, just the number? Yeah, well, why don't we just put here pH, the pH value, all right? But it's not just the pH value. What have I always been putting in front of it? A negative, 10 to the negative pH. Let's do some example calculations here for a moment. Let's start with figuring out the H3O plus concentration. So I'm going to change colors here. I'm going to put example. I'm going to put here, determine the concentration of H3O plus. And we'll start with A, and the pH equals, and we'll just make it 5. H3O plus equals, this is pretty easy business, I hope. Pausing for thinking. What's the H3O plus? Yep. 10 to the negative 5. B. What if I had a pH of 2.78? H3O plus. Well, in terms of what we've been doing, give me the equation that I need to figure out. In other words, just do the same thing as we did here, and then I'm going to show you how to use your calculator to get an actual useful number. What's this going to be? Yep, Jenna? 2.78. All right. At this point, on your calculators, you are going to locate a button. It's usually the second function log, and it's going to look like this, 10 to the x. Can you find the 10 to the x button? All right. So now at this point, you're going to press the 10 to the x button, right? So press 10 to the x. I'll make it into a button. And then put your negative 2.78. You may have a reverse calculator, and you might have to do this all in reverse. You might have to do 2.78 negative, then second function log. But if you've got a calculator that runs in forward, then you can do this forward, and you will get a number that is now a decimal number. It'll be a small one. What do we get? Yep. 166. Excellent. And that's in moles per liter. Anybody not get that? Everybody's able to get that number? Let's do one more example then. What if the pH is 11.2? Three significant digits again. This time you should be presented with some scientific notation because it's going to be very tiny. It means, notice here, this means -5. This means like 0.0000, right? This was -2. Here's our 2. This is -2, almost -3, 0.00. That means this thing has to have like 11 zeros in front of it. That's not going to fit on your calculator. Do you have an answer? What do you got? -12 moles per liter. One more digit would have been nice, but it's okay. We can leave it there. All right? Let's now do some calculations with pH. Determine the pH. A. H3O plus equals. I'm just making this up as I go. Let's go with 1 times 10 to the -8 moles per liter. Now this one was designed to be an easy one. 1 times 10 to the -8 is really the same as 10 to the -8. And when we determine the pH, right, negative log of 1 times 10 to the -8, remember the pH, the P takes the power off of the exponent. and the negative gets rid of this negative. What's the answer to this? You can run it through your calculator, but there is an easy way to do this. But you could run it through your calculator. I don't care which way you do it. What do you got? Taylor, what do you got? 8. That's a terrible 8, especially under a log there. I won't make it an 8 there. That's even worse. I don't know how that makes that an 8, but it does. This 8 right here becomes our pH. All right? Now the question is, what if this isn't a nice 1? Because in my table up top, all of these guys up here, right, that I just write as 10 to the negative 3, it's actually 1 times 10 to the negative 3, right? So what if it's not a nice 1? What are we going to get there? Well, let's do some examples on that. B. pH3O plus is, again, I'm just making it up, 2.76 times 10 to the negative 3. So pH is 2.76, sorry, it's negative log. Thinking ahead, getting rid of this. Negative log of 2.76 times 10 to the negative 3. Now, before you press the equals, you should have a guess on what number it's going to be close to. Because if it's 1 times 10 to the negative 8, then the pH is just 8. I take the power off of it, right? If this was 1 times 10 to the negative 3, what would we expect the pH to be? 3. So that means we've got to be close to 3. This number 2.76 is actually between 0 and 10. If this number became a 10, then this would become negative 2, because I'd have 10 times 10 to the negative 3. 10 times 10 to the negative 3 makes it negative 2, okay? So any number other than 1 is going to bring the pH from this exponent closer to the next one that's up, to 2. This has to be between 3 and 2. It has to be. If you don't have it between 3 and 2, you've got a mistake. That's a check. That makes sure that you know how to do this. So the way I always do this before I even put the number in is I look at this, I say, all right, I got to be close to 3, and this is bringing me closer to 10 to the negative 2 because it's going towards 10. So it's between 2 and 3. It's got to be between 2 and 3. And that's a quick check all the time. So what do we have as our answer? Yep. 2.56. Okay? Let's do some more examples. I'm going to just keep writing a few more examples down, and then I'm going to give you a little worksheet to try. Actually, we're going to talk about a few other things before I give you the worksheet. C. H3O plus is equal to 5.23 times 10 to the negative 9. And that's moles per liter. By the way, these are all moles per liter, all these concentrations. Moles per liter. Go ahead. pH, negative log. 5.23 times 10 to the negative 9. Even before we write it down, what's it got to be really close to? What's it going to be close to? Yep, 9. And it's actually going to be moving closer to 8 because of the 5. That's kind of almost to 10, halfway to 10. So it's got to be between 8 and 9. It's always going to be one number lower than that exponent, between 8 and 9. And what do we have for a number? Yep. 8.28. Everybody getting that? Is there anybody not able to get these numbers from your calculator because calculators all behave differently? We're okay? All right. Let's do one more example. D. The H3O plus concentration is 2.67 moles per liter. No exponents, just straight 2.67. No times 10 to the negative. It's a highly concentrated acid. Highly concentrated. pH equals. Again, don't wait for me at this point. Negative log of, da-da-da-da, get the calculator out, da-da-da-da, run it through. Negative log of 2.67. And if you're looking at the number saying, huh? Really? Can it be? Yes, it can. It can be. What's the answer? Yep, Taylor?
I got negative 0.43.
That's correct. I think it's correct. Is the number correct? Negative. You can have a negative pH. Remember at the top I said that if you have a concentration of 1 mole per liter of H3O plus, it's 0. If you have a concentration that's greater than 1, it puts you on this side of 0. It means you can have a pH of a negative pH. That's valid. Something that has an H3O plus of 2 point something something. All it has to do is have to have a concentration of greater than that particular value. I could make a hydrochloric acid solution, all right, and actually our super strong hydrochloric acid solution that we get that's concentrated is 16 moles per liter. That's going to be way beyond. That'll have a negative pH. That'll have a negative pH. Now our pH paper will not show a different color beyond that because it's only designed to go to that lowest level. I've never put a pH probe into something that strong because I'm afraid to damage it. But according to the theory and the mathematics, it would have a negative pH. Yeah. Okay? All right. Are we comfortable calculating pH? I think so. Let's then stay back at the top of this calculation here for a moment, of this picture here. And you go back to this picture because I'm going to ask you to add some stuff to this picture. And let's now talk a little bit about what this H3O plus concentration would be. Let's say I pick this number here. What is this? 12, 11, 10. So let's have a 10. And again, we were getting pretty good at this. We could put it in the equation, but we don't need to. What's the H3O plus going to be here? 10 to the negative 10, right? Not that we're doing anything new. Now, the reason I've done this is because this is a little strange. We're now realizing that we can use our pH equation and our H3O plus equation, and we can determine that we actually get a little bit of the H3O plus in water in a basic solution. And that's a little different. That's a little strange. I can even do a calculation for here. At a very strong base, I can actually put that 14 into there, and I can get 10 to the negative 14th. It means that in a base, there's actually a little bit of acid. Now, where's that coming from? And now I want to explain why this strange thing is happening. So what I want to do now is, let me take a different color, and underneath the H3O plus sign, I'm going to put an OH line here, OH minus. I'm going to write it on this side because it's close to the base. Okay? And it turns out that in water, there is also 10 to the negative 7 OH minus. Neutral isn't what you thought. Neutral is when we have those equal amounts of acid and base in water. Not that they're gone, but that there's an equal amount and that there's a very small amount. Okay? Now there's a very special equation that exists for water, and you can now write this. If you don't have any more room, you can write this underneath somewhere. But it turns out that for all aqueous solutions, whether they're neutral, acidic, or basic, it doesn't make any difference. It turns out that if you take the concentration of the H3O plus and multiply it by the concentration of the OH minus, you get a special number which is 10 to the negative 14. That is a special property of water. All right? The reason it does this is because water can do something called autoionization. Autoionization. ionization. Water can do this maneuver, H2O plus H2O to produce H3O plus OH minus. What that means is, in all aqueous solutions, water itself is playing the game. Remember we talked about the game and how acids are good at getting rid of their H's and bases are good at gathering up H's. It turns out that in pure water all by itself, it's as if the water molecules also want to play the game. Oh, hey, there's no acid or base around. Hey, you want to play? Keep away? Sure, let's play. And one water molecule bumps up to another one and says, I got your H, making an H3O plus and an OH minus. And for every H3O plus that's formed, an OH minus is formed. Now, it's not that this happens a lot. In the water, if you were to take a sample of water, the amount of H3Os and OHs that trade, you multiply it, you get 10 to the negative 14. So it's a very small amount that does this, but it does it, all right? And this is true in all aqueous solutions, whether acid is around or whether base is around. So what that means is there's always a little bit of H3O plus and a little bit of OH in all aqueous solutions, in all water. Let's go back and take a look at our pH scale. Here we've got this situation, 10 to the negative 7, 10 to the negative 7, neutral, that's that balance point. But if I head over now to acidic, what happens is when an acid is added, I end up with more H3O plus. But correspondingly, right away, there has to be less OH minus. As the H3O plus goes up, the OH minus goes down. And these two numbers always have to add to negative 14. So if this is negative 3, I'm going to have 10 to the negative 11. So as the acid goes up, the OH goes down automatically in all aqueous solutions. Over here, if I've got 10 to the 0, right, then this is going to be 10 to the negative 14. In a strong acid, there's a tiny little amount of OH. It's so tiny we don't even worry about it. That's why we don't even talk about it. And over here, if that's 10 to the 10, this is 10 to the negative 4. So when we go to the base side, now the base begins to dominate and the H3O plus goes down. Okay? And over here, how much base am I going to have? 1, which is the same as 10 to the 0. Now notice, I have a pH scale up here, okay? And it comes from these numbers, but there's no reason I couldn't have an opposite scale below it. What would we call a scale that looks at the concentration of OHs instead of H's? What would I call that scale? This scale underneath would have a number of 14 down below it. This would have a number of 11. This would have a number of 7. This would have a number of 4. This would have a number of 0. But it wouldn't be the pH scale because it's not looking at the power on the H3O pluses. It's looking at the power of what? What's the substance that we're looking at down here? Yeah? OH. We can have something called a pOH. There is something that we call the pOH scale, and it looks at the concentration of OHs, not the concentration of H's. Let me flip to the next slide again. I want to write now underneath here. pOH is going to be equal to what? Well, what do we calculate when we calculate the P whatever? Doesn't matter what it is. I know it's difficult for you to answer because you've now just discovered that there's this crazy bizarro world of OHs rather than Hs. And in your mind, you're all distraught because you've learned so long about pH, and now you're realizing, what? There's this other base world that exists out there that's just the complete opposite, and it's true. Once you get over it, though, the math becomes really easy. What's the equation going to be? Yeah, what's this equation for pOH going to be? OH minus. I've got an equivalent OH minus equation over here. That's just like the other one. But I was looking for the pH equation first, but I don't care. What do you got there, Amy? 10 to the negative pOH is how I can figure out the OH concentration. That's good. But what if I want to get this exponent off of it? How do I pull the exponent off? What's its equation going to be? It's just like the H one, except it's bizarro world. Yep. Excellent. That's exactly correct. That's true. So we now know how to deal with bases. Now we can deal with bases if we get some concentrations. Now there's one last little special equation. Let me switch back to the slide here. Whoops. Even though I've just introduced you to this crazy bizarro world of a pOH, right, world, at a pOH scale, we still like to talk in terms of pH, because that's the cool one for some reason. That's the one we all learn in grade 9 and 10. You know, you always hear it, if you're talking about Dove soap. It's not just soft on your skin. It has a pH that's adapted for sensitive skin. And then they'll dip some litmus in it, and it'll show that it's 7. Oh, they'll never say, oh, and it also has a pOH of 7. That's good, too. And people will go, what? What's a pOH? I don't know, right? That's because nobody talks about it. It's like a secret chemistry society of the pOH world. But we do need to still flip it back to pH. Take a look at this relationship between pH and pOH. If this is my pOH scale down here, notice pH, pOH, pH, pOH, pH, pOH, pH, pOH, and there it is there. What's true always about the pH and the pOH? Yep. They always add to 14. So if we know the pOH, we can quickly flip it to a pH. Now we can deal with bases, find pOH numbers, subtract some 14 off of it, and get the pH. So that's the last link in the whole chain here. We can say here then that pH plus pOH is equal to 14. Okay? So now let's do a few examples on this. Let's do example 1. All right? Determine the OH minus concentration. And I'm going to say the pH is 3. Now, the first thing we need to do in this solution is figure out what the pOH is. It's always 14 minus the pH. 11. 14 minus 3, 11. So we have to do an extra step. And now we can then say then that the OH minus concentration is 10 to the exponent, what? Negative 11. That one doesn't even need a calculation. 1 times 10 to the negative 11. Not that exciting. Okay? Let's do one more example of this. Something that isn't so nice. B. What if the pH was 12.7? First thing you've got to do is determine the pOH. and then you can put that into your exponent. And what is that? What is the pOH? You got a pOH first? 1.3, 10 to the negative 1.3. And did you run that as well? Don't clear your calculators out, folks. This is where we take a lot of numbers and carry them on to the next one. If you've got that answer function, right? 10 to the negative answer equals, gives you the number. You know what I'm talking about? The answer function? Yeah, use that. It's a great thing. Got a number? 19 point, did you put the negative in there? If you don't put the negative in there, then you get a big number. We want a little number. What do you got? 0.05. It'd be nice if we had another digit. Is it exactly 0.50? 0? 50, okay, 0.50. And again, that's a moles per liter. Okay? You can't get that, you can't get the 10 to the negative 1.3. I'm going to give out a little worksheet in a moment. At that point, I'm going to walk around and I'll fix up some of these problems. Okay? Let me just do a few more examples and then I can let you have the worksheet and then we're going for a bit. So let's do, again, example 2. Let's go with determine the, and again, we seem to always want pH. Even though we're talking about bases, we want pH. So I'm going to give you an OH concentration. The OH concentration is 2.7 times 10 to the negative 3. How's it going, Jamie? Moles per liter. So in this case, what's the first thing you're going to get? If I give you an OH minus, what's the first thing you have to calculate before you can get a pOH? Or sorry, a pH. I just gave it away. Before you can get a pH, you have to have a pOH. You do the pOH just like you do the pH, except you're using the OH numbers. Negative log 2.7 times 10 to the negative 3. Again, we can make a guess. The pOH should be close to what? What should it be close to? 2 and 3. So what do you get? It's got to be between 2 and 3. Yep. 5.7. All right. But we're not done because now we want the pH. And the pH is also the same as the flip side. It's 14 minus the pOH. This time we're flipping it over. Don't clear your calculator. 14 minus answer equals, yep, 11.43 is the pH. I want to do one more example here, and then I'm going to give you a little worksheet to work on for a little bit, but then we want to now bring back in our percent ionization. We're going to do one where we're going to do both yesterday's and today's. We're going to bring it all together. OH is equal to, and let's make it 3.7, and that's it. No times 10 to the negative moles per liter. A very strong, look at that, that's terrible. A very strong base. So we're now going to get some silly numbers again, but that's okay. Follow the calculations and you'll be fine. What do we get for a pOH? And yes, you're going to get one of these numbers that you didn't think could exist, and they definitely can. pOH, what are we getting for a number? Yeah, Jenna? Okay. And now pH is going to be, and again, don't even worry about that negative. 14 minus answer equals, we'll take care of it. 14 minus a negative number means you have to add it, but if you just go 14 minus answer equals, it's going to have the negative with it. What do we get for a number? Yeah, Jenna? 14.57. And yes, you can have a pH beyond 14. It just means it's a really, really, really strong base. I know that concerns some of us. Don't be concerned. All right? At this point, I have a little bit of a worksheet, and I'm going to just stop this thing for a second.